Okay, so welcome to this part two of data analysis. In part one, we looked at qualitative data analysis, everything we need to know about that. And today we are looking at quantitative data analysis. This is a very broad topic, all right? I thought of creating a series from this, but I do also want to have a lot of videos on just one thing. All right, so I'm going to combine this into one. I'll not really go into details in some aspects, all right, so that the video wouldn't be so much. All right, so let's zoom into action. So quantitative data analysis, basically we are looking at numerical, right, numbers. So what is quantitative data analysis? It's a process of examining numerical data to describe a population, to compare groups, to identify relationships, test your hypothesis. That was in your chapter 1, right? Make predictions using statistical techniques. Okay, so a simple example, if your lecturer wants to know whether class attendance affects your performance, all right, you collected the data from individuals, so student A through to student D. These are their attendance. Student A came for 90% of the time, and then his exam score was 85. Now the one with the least mark was 45, came for 45, and then his score was 50. Now at this point, you can see that these are just numbers, right? But then when we analyze it, it converts these numbers into answers for us, all right, to appreciate what we are seeing with just these numbers. So there is a roadmap to this quantitative analysis. First of all, you have to define the study, right? You should have a research question. That has been one thing we have been echoing throughout the chapters. Everything points towards your objectives. Everything points towards answering your objectives, right? Good. So that is no different when you are answering your when you are analyzing your data. Sorry. So you define your objective. You look at the variables, right? Identify the variables that you are going to collect. Gather the information, that is collecting the data, and then you clean the data. Once you clean the data, you then describe your data, right? Describe it, add meaning to what we are seeing as numbers, and then you check assumptions. After you check assumptions, then you analyze your results, right, by applying inferential statistics. That is what most people actually like, most students like. From there, then you interpret your results. Okay, all right, so we'll be taking each of them one after the other. So you have to understand what variables are. Now, variables are any characteristic that can vary from one person to the other. That can vary from a situation to the other, right? So rainfall, for instance, is a variable. When you go to the northern part of Ghana, it doesn't really rain much. But then when you come to the Ashanti region, because of the terrain, we have more rainfall there. So rainfall becomes a variable. It varies from one place to the other, one situation to the other. An example too is age. Age varies, height varies, income varies, your blood pressure varies, okay? So these differ among individuals. So you have to understand the variable types we have, okay? You have to understand these variables. The first one we are looking at is the independent variable. Okay, others will say that the variable that is influencing or causing that variable. An example, study hours. The question is, does study time affect academic performance? Now, what is the output or the end goal? The end goal is academic performance, right? And then what is causing academic performance, or what is influencing academic performance is what? Study time. So now your study time or your study hour becomes the independent variable, the cause of academic performance increasing or decreasing. All right, so that is independent. And now dependent variable I've explained already. So now academic performance becomes your dependent variable, or the results of the course. Okay, so your outcome. So the same example, now academic performance is your dependent variable. Now, this is something simple to let you remember. So when you ask, what am I trying to explain? It means that that is the dependent variable. We are trying to explain an outcome. Now, what might be causing this outcome? That is the independent variable. So this is an example for you to look at. Okay, so we look at some levels of measurement. Now, this is where the decision for the statistical tool begins. Okay, so we have the different types of data as well. For this one, we are looking at nominal data. Okay, nominal data, where categories are in no order. We have no order or no degree in its presentation. So an example is sex or gender. So we either have male or female, right? That is it. We don't have any other thing after this. Now, religion, we either have Christian, Muslim, all the other religions, right? There is no order in this. Marital status, you are either married, not married, separated, cohabiting, all of these instances. Faculty, you are either in the department, faculty of health and allied sciences, or faculty of engineering. You see? Good. Now, one thing you also have to note about nominal data is that neither is greater than the other. Okay, but when you talk about ordinal, the name is even implicative. There is an order, there is some kind of hierarchy or ranking, right? So, for instance, satisfaction, you are either poorly satisfied, fairly satisfied, you are excellently satisfied. Wow, I'm skipping good because I don't know whether you have goodly satisfied. All right, that's just by the way. So that satisfaction, there is an order, right? And then frequency, for instance, more frequent, less frequent, no frequency at all. So when you look at all these data points or data means, you realize that you can categorize them into nominal, ordinal, and there is a last one, continuous. Data can also be continuous, where they are only numerical measurements. So age is a continuous data, height is a continuous data, your income is a continuous data because, right, it deals with numbers. Scores also are continuous data. Now, data cleaning is also very important in data analysis. I cannot overstress this. Right? It is very important. Okay, it's one form of quality assurance, data quality assurance. You have to clean your data and make sure they have been harmonized. Okay, so for instance, this is a dirty data or a raw data. Student A has the age 20, B 21, and C 250. This is very alarming, right? It's very alarming. Not that it is impossible to have someone living up to 250 years. Currently in her dispensation, this is not possible. Okay, good. So it means this is clearly an error. All right, so what do you have to do to clean this data? You go to your questionnaire or your primary source of data collecting tool, and then you cross-check, you verify, and then clean it. All right, you are not changing the results, and so you are not falsifying. Okay, what you are doing is you are cleaning, you are trying to provide the correct or the accurate information. This could have been an entry error, data entry error. Okay, so that's just by the way. Now, common problems with data, right? You have missing values. I mean, sometimes you miss entering a particular data. You have the person's name, the person's age, and then you forget to take the person's hometown. To your study, that information is vital. Okay, that forms part of the demographics, and it will have an important impact on your work. And so missing values affect your data. Duplicate entries, you could have the same person come into the same facility, you are picking the data twice. That is duplicate entry, right? And then impossible values, as you've seen, also up there. Coding errors. Now, you just need one way of coding. If you said, okay, my coding dictionary is such that males, I represent them with 1, females, I represent them with 2. You shouldn't go again and say, okay, males, you are representing it with M and then females with F, all in the same data set. That is going to cause problems. Okay, so you make sure you are coding, you're having just one code for one variable. Okay, good. So the next step is descriptive statistics. The first thing you actually do in terms of analysis is descriptive statistics, and usually they form part of the demographic section of your collection, your data from the participants, right? So you want to describe, okay, the data, and usually we use frequencies and percentages. Okay, so an example is frequency for males. Out of 300 participants you recruited for your study, 120, when you strike the percentage, let's say 40% were males, and then 180, which forms 60%, are females. That is even represented here. Now, the next thing is to look at central tendencies. Now, this describes how centered your data is, and you have a lot of them. You look at the mean. The mean is the average. Out of these 5 scores, when we strike the average, we have the mean to be 80. Now, median is the middle value. Once you arrange the values from the smallest to the highest, and here we have 50 being the middle value, and mode, the most frequently occurring value. When you look at this, the most frequently occurring value is 60. Now, these things can be calculated manually, but now with statistical tools, we have these being generated easily. You input your data, you analyze it, and then it gives you your mean, your median, and then your mode. Okay, so which measure should you use? When do you know how to use mean, and when do you know to use median or mode? Now, mean are best for normally distributed data, and then its alternative is median for non-normally distributed data. Now, if you want to identify a common category or value, then you use the mode. All right, so basically that is how you should use these. So briefly, an example: if you want to calculate the mean, you find the average of these values, right? You find their average, you get the mean. Now, the median, you arrange all of these from in ascending order, and then the middle value is what is your median. From your central tendencies, you look at measures of dispersion. Okay, so for measures of dispersion, it just describes how spread your data is in terms of your mean or your true value. So an example is the range from highest to lowest. So the highest value is 80, the lowest value is 20. So we have our range to be 60. As I mentioned earlier, all of these things could be calculated for by the statistical tool you'll be using. Standard deviation just tells you how spread your data is and how close it is to the mean score or your true value. So suppose two classes have the same mean score, right? When you calculate this, you calculate this. Both have similar means, but class B is much more spread out, right? We have the highest here being 110, highest here being 72, lowest being 30, lowest being 68. So we have this spread, class B having its scores spread more apart from the mean. All right, so we can say that class B therefore has a larger standard deviation. Okay, a larger standard deviation. Now let's take it a step further. What does standard deviation tell you? It just tells you that your observations are clustering around the mean, or they are clustering widely above the mean, right? So if you have a smaller standard deviation, which is really good, it means that your data are clustering around your mean. They are closely in line with your true value. Okay, good. And it also means that the participants are similar. Larger means participants greatly differ. If it is income, we are looking at participants differ greatly with income. We have the lowest 20 and then the highest 300,000, right? But if they have smaller standard deviation, it means that they have similar income. So that's the importance of standard deviation. And usually parametric tests, you remember when you use mean when it is parametric or normally distributed data. Usually means are reported in addition to standard deviation. So you have your mean and then into brackets standard deviation. For medians, median and then interquartile ranges. Okay, that is for non-normally distributed data. Okay, so data visualization, right? Before any statistical test, you can use data visuals to explore your data, right? Before you start testing it to give you a fair idea. Now, for bar charts, they are best for categorical variables. We'll talk more about categorical variables as we move on. All right. So, example, sex, it's in category. You are either a male or female. So, these are categorical variables. Faculty, whether you are in this department or this department. Marital status, married, divorced, cohabiting. You see, they are in categories. Now, we have pie charts. They show proportions, useful but usually overused. All right, when you are talking about proportion of something, so 25% of males were represented in your work. I mean, it is better to use pie charts rather than the bar chart, okay, because it's showing proportion of a whole, right? As we can see, it's showing proportion of a whole. Now, histograms are very important in determining whether your data is normally distributed or not. Okay, once you run a histogram, it will either taper to the end, to the left, or skew to the right, or be normally distributed. So that is one way you can check to see whether your data is normally distributed or not. By normally distributed, we mean parametric. They are the same thing, all right? Either parametric or normally distributed data. And they are usually used for continuous variables, not categorical. So you can't use it for sex, male and female. No, you can't use it. You can use it for age, which is a continuous variable, right? Where we have different values, right? Different variable with different values. Same for exam scores. And then we also have box plot, one of the most powerful graphs. It is able to show you the median, how spread your data is. If there is any outlier, you can see it in there, right? You could see that a particular data is very much outside those that are centered around one region. So you can know right from there that that is an outlier. Okay, so this gives us some of the tests. We have some of the visualizations we have. So you have here your bar chart. This is your histogram. This is a normally distributed histogram, right? This is a skewed histogram. This is a positively skewed histogram. Okay, we have your pie charts. These are all pie charts. Okay, we have others. This is a line graph, and we have a number of them, right? So each and every one of them has when we use them. Let's move on. So now, what you have learned so far is describing your data. We have not yet tested anything, right? We have not yet answered, is the test significant or not? Is there a relationship? Is one factor affecting one or the other? Now, if you want to know these, then you have to get into the next one, which is inferential statistics. Okay, but before we enter into inferential statistics, you have to understand that every statistical test, you have to get the assumptions and then know whether it is parametric or non-parametric. Okay, so when you determine it is parametric, you have to know test to know that your data clearly assumes or clearly satisfies the assumptions of that particular test before you apply it to your study. Else you will get data all right, but then it will not be an accurate data. It will be a misleading data. We move on to the inferential statistics. Now, what is an inferential statistics? We know that descriptive just describes your data, but inferential statistics help you to make your conclusions. Okay, helps you to make your conclusions. All right, so example, we have a mean GPA for males 3.2, for females 3.5. Is this difference real or it is happening by chance? Now there is a difference of 0.3, right? Is it real or it is happening by chance? And this is when inferential statistics are important. But why, someone will ask, why can't we just look at the numbers? 72 and 75, a difference of 3. Looking at this, you would think that females were outperforming males, right? But that's not true. It could happen that the sample size for your study was even very low, and so these findings, you cannot generalize your findings. All right, you are not confident enough to generalize your findings because the sample size is small. I mentioned this in the methodology. And it could also be that the difference occurred randomly. There could be other factors even contributing to these figures, right? So inferential statistics is very important when you want to look at this. And nearly all inferential statistics begin with hypothesis testing. I spoke about this in the chapter 1, hypothesis testing. All right, we have the null hypothesis and then the alternative hypothesis, where the null says there is no difference. The alternative says there is a difference or there is a relationship. Okay. Now, before choosing a test, you have to know whether your data satisfy the assumption required for that particular test, and not that you should run this test or not. Okay, you should know whether the assumptions are met. One assumption is normality. So what is an assumption? An assumption is a condition that should be reasonably satisfied before using any statistical method. Okay, before you use any statistical method. So it's like a requirement to have a work done properly. Everyday example. Imagine you are applying for a driver's license. There are requirements, right? Even applying for school, there are requirements, there are cutoff points, there are courses you should have taken in school. Okay, so all these are what we call assumptions in statistical terms when it comes to statistics. Okay, all right, so now we move on to what we are all waiting for: parametric and non-parametric tests. All right, now parametric tests, they make assumptions about the data. Okay, and that is when you know the test to use. I'll skip this and we'll talk about them later. So parametric tests are important because when assumptions are met, they make your data or your results more powerful, better at detecting true differences, and then more precise estimates. All right, non-parametric tests, they require fewer assumptions. If it doesn't meet parametric, automatically it meets non-parametric tests, and these are some of the tests you perform. Now, they are useful when your data is not normally distributed, that is, they are skewed. Your sample sizes are small, your data is ordinal, or assumptions for normality are violated. Okay, so the most important assumption, if you even don't remember any of them, as I mentioned some few seconds ago, is normality. Is your data normally distributed? Okay, is it normally distributed like this? Right? Is it normally distributed? This is a normal distribution where we have our median close to the apex of the dome shape, median the same, mode the same, everything is in the middle, perfect symmetry. Now when we have a negatively skewed data, and with this you can see that all of these central tendencies are shifting. The mean is closer to the negative side, the median is somewhere in the middle, the mode is somewhere outside. And so the statistical inferences you are going to put out across with non-parametric data analysis, you could see that it's not really more precise. Okay, so that's why we said here parametric tests, they are more powerful. They detect true differences and more precise estimates because everything is in the middle. But then for negative or positively skewed, these three variables are just all over the place. Okay, now let's move on. I've showed you what parametric test looks like. Now an example of a normal data, student heights. All right, you can see that most values cluster near the middle. They are arranged in ascending order, and then most of the values are around 180, 150. They are not widely dispersed about the mean. But when you look at this, least is 500, maximum is 20,000. They are widely about the mean. Okay, they are widely about the mean, and so this is an example of a skewed data. All right. Now, why does normality matter? If the data is not normally distributed, results may become unreliable. This has been stated already, and so you have to check normality. Earlier, I showed you that histogram can be used to check for normality. Now, there's another one called QQ plot, which is also a plot that could also show you whether your test data is skewed or not. We have Shapiro-Wilk test, all right, most commonly reported. And if normality assumption is satisfied, if p-value is greater than 0.05, it means that it is satisfied. But if it's less, assumption is violated, and so you can't use Shapiro-Wilk, you use a different test. Now, assumption 2, homogeneity of variance. This just means that when you look at the male's results, right, we have 3 to 3.4, that's the range. For females, we have 1 to 4. The variance, one group is much more spread than the other. So it means that there is a violation of homogeneous nature of the variance, right? 3.4, this is okay. But then once we add this group, we have 1 and 4. This is widely distributed, okay? So this violates homogeneity of variance assumption. Okay, now how to test for homogeneity? How to test for this? We have the Leibniz test, okay? The Leibniz test, and when you test it, if the p-value is greater than 0.05, sorry, it means that assumption of homogeneity of variance is satisfied. Otherwise, it is violated. Independence and assumption. Okay, if one variable has an effect on the other, it means they are not independent, and so that data does not meet independence assumption. All right, so a good example is 300 students each complete one questionnaire, but then you have 100 students complete the questionnaire 3 times. It means that all the responses are not from one person, because one person failed it 3 times. Okay, good. So linearity, it just means that, as an example is, as study hours increases, that CGPA increase as well in a straight line, or there is a curve somewhere. And then outliers, I've mentioned this already. This is a huge figure when compared to the others, so that's an outlier. How to detect outliers? You can use box plots, I mentioned earlier, scatter plot as well. You could see that one figure or one data point is not near or where the other data are clustered. All right, now the decision process. You should have a research question. You identify your variables, you determine the type of data, you check your assumptions. If your assumptions are met, you do a parametric test. If they are not, you go on with non-parametric test. Okay, so let's go to the last part. So what's the secret in choosing any test? You have to ask yourself 4 questions. What is my outcome variable? That is your dependent variable. What is the outcome variable? Continuous, ordinal, or categorical? That is going to help you in your selection. How many groups are you comparing? None, 2, 3, or more. Do the assumptions for parametric test hold? If you answer these 4 questions correctly, selecting the test becomes very easy. All right, so let me go through again. What is my outcome? Is the outcome variable continuous, ordinal, or categorical? How many groups am I comparing? And do the assumptions for parametric test hold? All right, so then this is a decision tree. This is a decision tree, right? So you have your research question, you identify your outcome variable, you check the variable type, ordinal, categorical, or continuous. You determine whether there is a group that you have to compare. You check your assumptions, and then you choose your test, right? So let's use an example, one scenario. And with this one, we are looking at comparing 2 independent groups. Okay, 2 independent groups. So suppose your lecturer asks, do male and female students have different CGPAs? Sex is a categorical variable, right? Male or female. CGPA is continuous because they are numerical. All right. So if assumptions are met, then you are looking at 2 groups, 2 independent groups. Okay, then you have to know that you are going to perform an independent sample t-test. and then the purpose is to compare means between two independent groups. Okay, so you use sample t-test to run an analysis when you are comparing means between two independent variables. Now, if the assumptions are not met, you have to use Mann-Whitney U-test. Okay, this is a non-parametric alternative to the samples t-test. All right, so this is a summary of comparing two tests, two groups, and the test to perform. Now, scenario 2, same participants measured twice. So we have one participant, and let's say we have two test kits, right? We are trying to see which one is more sensitive. So one participant, two measurements, right? So you have, when your data meets parametric testing, all right, what you will do then is you will run a paired sample t-test, right? Paired sample t-test. So it is from the same patient, but then different methods for detecting that particular thing. Okay, so let's say you want to check whether a particular weighing scale is able to pick correctly the weight of a particular person, right? So you pick the same person you are weighing on different scales. So you use paired t-test to run that. Or you have a pre-test and then a post-test. The same individual, you have two results for. So you compare to see whether there's a significant increase or decrease, right? So that's for that. And its or non-parametric alternative is a Wilcoxon sign rank test. Okay, I'm rushing through this so that this video does not extend. Now, when you are comparing more than three or more groups, then you know that you are going to use ANOVA. That is when the assumptions of parametric is achieved. Okay, then you use ANOVA. Now, once you use one-way ANOVA and there's a significant difference, you don't leave it there. You run a post hoc test, and that one you use to key Bonferry or Scurf, right? And that will help you to identify which group differ, because you are looking at more than three or more groups. Okay, good. So an alternative to ANOVA is Kruskal-Wallis test, right? Now, when you want to look at relationships between two continuous variables, so a continuous variable, age and income, right? These are two continuous variables. If you want to determine whether there is a relationship, right? What do you have to do? If it is a parametric, if it meets parametric assumptions, you use Pearson's correlation, right? An alternative to this, when it is non-parametric, is Spearman's correlation. All right, good. I don't want to go into details, that's why I'm skipping. Okay, so when you want to look at association, now not between continuous variable, but between categorical variables. So we have sex, male and female, and then let's say religion, right? So you want to know whether gender affects a religion, or gender contributes to you selecting a particular religion, right? So these are both categorical variables, and what you would use is the chi-square test if it is a parametric data you are looking at. If not, what do you use? You use Fisher's exact test. All right, Fisher's exact test. However, with chi-square test, you have to make sure that with this assumption, expected cell count should generally not be too small. A common rule is most expected count should be at least 5. Anything less than 5, you use Fisher's exact test instead. All right, good. Predicting an outcome. Which factors predict academic performance? We have a lot of independent variables that can cause this dependent variable outcome. We have study hours. Study hours can cause your academic performance to increase or decrease. Attendance in class, same. Your age, all right, can predict your academic performance. Internet access can also have an effect on academic performance. So now, once you want to test to see whether any of these has an effect on academic performance, you have to run what we call multiple linear regression. It tells you which factors matter, how much they matter, and which remains significant after controlling for others. So here I would want to talk about confounding variables. So first of all, let's say in your study you wanted to determine whether study hours has an effect on academic performance. You run your analysis and then you realize, okay, there's a significant difference. Your general understanding is study hours significantly affects your study performance. But then there is a catch here. Attending class most of the time too can also increase your performance. Sleep duration can also increase your performance. So when you have this in your study, it means these are confounders. They can have an effect. And so when you are working on just study hours and you have a significant difference, you shouldn't just say that, okay, that is it, and so you are good. No, you have to go ahead. The moment there is a significant difference, you go ahead and run a regression analysis to know other factors that contribute to the performance of the students. All right, good. So as I mentioned, study hours appear important, but students who study more also attend class more. And so regression will separate these effects. All right, so I've talked about confounding. Another confounder could also be motivation. A student who is very motivated can learn even if they sleep less. They learn more, they sleep less, they have higher grades. Okay, so regression analysis can help you to determine which has an effect on what, by how much does it have an effect on the other, right? So that's very important. So this is a table that summarizes what has been said so far, and then there is a figure that I've created to help you to determine a test to conduct, right? Good. So I'm going to see whether I can add this image in the video description. If not, you just take your time to go through, take screenshots of it, and then make sure you understand the test you are running. So thank you very much for following us through data analysis. If you have any question, put them in the comments. I'll address them. Now, I was running through this because of time, all right? But if you send me a comment and there is the need for me to have another video, I will do that. So thank you very much. Bye-bye.